AquaMaster 3 digital output PO1 controlling a relay. AquaMaster 3 has 3 optocoupled MOSFET transistor outputs that can control a maximum of plus or minus 35 volts DC at 50 milliamperes. The AquaMaster 3 was designed to send pulse outputs to totalizers, but this video will illustrate how to electrically connect the output PO1, as an example, to control a relay with overvoltage protection. AquaMaster 3 has a special cable to connect to the outputs and data port. When properly installed, this cable seals the connector on the AquaMaster 3 and provides an IP68 rating for the transmitter. Relays and inductors must be snubbed or clamped to limit overvoltage conditions that can destroy the outputs. Snubbers are energy-absorbing circuits used to suppress the voltage spikes caused by the circuit's inductance when a switch, electrical or mechanical, opens. The most common snubber circuit is a capacitor and resistor connected in parallel across the switch or transistor. The time constant of the snubber circuit should be small compared to the shortest pulse on time. Most relays have variations that have built-in snubbing circuits, but there are those on the market that do not. When driving a relay with AquaMaster 3 digital outputs, they must be protected from overvoltage conditions. These overvoltage excursions will destroy the driving transistors of AquaMaster 3 digital outputs. This video will offer common methods used to limit these voltage excursions. All relay manufacturers publish the specifications for relays. With this information and your application requirements, calculation of the snubber values is simple. Knowing the open circuit voltage, switching frequency, and coil characteristics of your relay, the RC values can be determined. A 680 ohm resistor in series with a 6.8 microfarad capacitor wired across terminals 41 and 42 will snub the voltage excursions caused by the relay coil. Before snubbing the transistor, the voltage excursions exceeded the max rating of the transistor. After the snubbing circuit is installed, the response is slowed and the voltage excursions are limited to safe values. RC snubbers are effective but have limited frequency response due to the time constant. For inductive loads, flywheel diode configurations are more practical. When the transistor turns on, current flows through the relay coil, establishing a magnetic field. When the transistor turns off, the field collapses, inducing current through the coil. This current creates the overvoltage condition that destroys the transistor. The diode across the coil will begin to conduct the current back through the coil when the voltage reaches the forward conducting voltage of the diode, usually less than 1 volts DC. When the transistor turns on, the current passes through the coil, through the drain source junction of PO1 to ground. The magnetic field builds around the coil. When the transistor shuts down, the collapsing magnetic field induces a current. Instead of building a voltage across the high impedance, the diode conducts, dissipating the current, preventing the voltage excursion. Diode selection is simple. It must be selected to block the applied voltage and be able to handle the peak current from the coil.
This is Cliff McEwen. Thank you for watching, and please subscribe to my YouTube channel for additions and updates. If you have any questions or comments, please contact me at abbwarminsterflowguys@gmail.com.